This is the video for section 7.4 on partial fraction decomposition. The point of this section is to teach us how to integrate rational functions, and this technique will allow you to integrate any rational function. So that's a function that's a quotient of two polynomials. And the big picture idea here is that you take an arbitrary rational function and rewrite it in terms of simpler ones that we know how to integrate using the techniques that we've developed so far in this chapter. The most general situation for partial fraction decomposition is fairly elaborate, so I'm going to build up to the general technique in a certain number of steps. So we'll start with a very basic case, and that's of the case where your function f of x is a linear polynomial on top, and on the bottom, oh, that's a bad choice of letter. Let's try something else. So the denominator I'm going to have be of the form ax plus b times cx plus d. And this is where a and c are non-zero and neither of the denominator factors is a multiple of the other. And then the numerator is going to be anything of the form ux plus v, where that numerator, let's make sure that that's non-zero. And the fact is that this function can always be rewritten in the form a over ax plus b over cx plus d for some numbers a and b. Okay. And then the point of this is that each of these functions, here and here, can be integrated separately. That's using a simple substitution to get the general rule that the antiderivative of a over ax plus b dx is a over a times ln of absolute value ax plus b plus c. So anytime you have one constant divided by a linear polynomial, that's something that you can take the integral of. And the point of the fact is that we can apply that in order to compute the integral of an arbitrary function that looks like this. So on the next page we'll see that in action. So I want us to compute, as an example, the antiderivative of x over the product x plus 4 times 2x minus 1. All dx. And so you have to note that this rational function is in the form that I described on the previous page, those denominator factors are not multiples of one another, and the numerator is a polynomial of degree less than or equal to 1. And so we can rewrite that integrand function using the fact from the previous page as some number a over the first factor, x plus 4, plus some number b divided by the second factor, 2x minus 1. And so what we need to do is we need to find out what a and b are. And the technique for doing that is to multiply both sides of the equation here by that entire denominator function. And when you simplify the left-hand side, those x plus 4 factors cancel and the 2x minus 1 factors cancel, and we get x on the left-hand side. The right-hand side you have to distribute the x plus 4 and the 2x minus 1, and what you end up with is a times 2x minus 1 plus b times x plus 4. Now, this equation is supposed to be true for all numbers x. So the way to solve it is to collect the like terms on the right-hand side. So that right-hand side simplifies to 2ax minus a plus bx plus 4b. And collecting like terms, we get 2a plus bx plus 4b minus a as the constant. And since that's equal to x, that says that the coefficient of x here has to equal the coefficient of x here, which is a 1. And the constant term here has to equal the constant term on the left-hand side, so this constant term is 0. So we get a system of linear equations, 2a plus b equals 1, and 4b minus a equals 0. I can solve the second one for a, and I get a equals 4b. Substitute that into the first equation, and we get 2 times 4b plus b equals 1. And when you solve that, 8b plus b equals 1. So 9b equals 1, and b equals 1/9. And then you combine that with the expression for a that we found in order to find that a equals 4/9. So that says that the integrand that I have on the left-hand side of the page here can be rewritten as we have 4/9 over x plus 4 dx plus 1/9 2x minus 1 dx. So that's taking the pieces that I have from my decomposition, putting in the values for a and b, and then breaking the integral into two pieces. And now, from the formula that I set on the previous page, this is 4/9 times the natural log of absolute value of x plus 4 plus 1/9 times 1/2 times the natural log of 2x minus 1, all plus c. And that's your answer. This method of using a system of linear equations that you see here on the right-hand side in order to solve for the constants a and b may be one that's not familiar to you. You may be used to another technique which is to simply take this equation here and plug in some specific values. So specifically, you would plug in x equals 1/2, and you would find that the left-hand side 1/2 equals a times 0 is what I get when I plug 1/2 into 2x minus 1, plus b times 1/2 plus 4. And if you solve that, you end up with b equals 1/9. And similarly, if you plug in x equals -4, and why am I choosing those two numbers? Those are the values that will make this factor equal to 0 or this factor equal to 0. So we get that -4 equals a times 2 times -4 minus 1 plus b times 0, and we end up with a equals 4/9. So if you like that technique, you're free to use it. Sometimes it works really nicely. Other times it might not work as nicely as you'd like. The system of linear equations technique is guaranteed to work, although sometimes solving those systems can be a pain in the butt too. Now, the general technique for rational functions where your denominator is a product of distinct linear factors looks like this. So your denominator is a product of linear factors. So the AI's are all non-zero, and no factor in the denominator is a multiple of any other factor. And the numerator can't be too big, so it has to have degree at most n minus 1. So if you have 5 factors in the denominator, your numerator can have at most 4 terms. And then the result is that this function can be decomposed as a constant divided by the first factor in the denominator, plus a constant divided by the second factor in the denominator, and so on. And for specific examples that look like this in more generality, I'll suggest that you look at examples 2 and 3 on page 486. Now, one thing to note about this is this assumes that the numerator isn't too big. What happens if the numerator is big? So if numerator has degree greater than or equal to n, well, then we have to use polynomial long division in order to reduce down to a fraction where the numerator isn't too big. And I'll show you how that works in the next example. So for instance, I want to integrate the function f of x equals x cubed plus x squared plus 2x plus 1, all divided by x cubed minus x. And we'll see what to do with that denominator in just a minute, but we already see that the numerator has the same degree as the denominator. So we'll do polynomial long division, which terminates quickly. So I take my numerator, divide by my denominator, and the technique for this is I have to ask what times x cubed equals x cubed, and that's exactly 1. So I multiply 1 times x cubed minus x, and then I have to subtract so now we end up with x squared plus 3x plus 1. And that, because it has degree smaller than x cubed minus x, is my remainder. And the 1 on top is my quotient. And what that says is that my function decomposes as the quotient plus the remainder divided by the original denominator. And what you notice is that this function is now one that has the numerator degree strictly smaller than the denominator degree. And so we can apply the technique of partial fractions in order to decompose that quotient, which we'll do over on the right, over here. So I'm going to consider separately the function x squared plus 3x plus 1 over x cubed minus x. Now that denominator factors nicely as x times x squared minus 1, so that's x times x minus 1 times x plus 1. I have 3 distinct linear factors in the denominator, so I can apply my fact from the previous slide to know that that can be written as a over the first factor plus b over the second factor plus c over the third factor. And now, if we do the same solving technique that we did before, let me not belabor the point on this. multiply both sides by x times x minus 1 times x plus 1, we get x squared plus 3x plus 1 equals a times x minus 1 x plus 1 plus bx x plus 1 plus cx x minus 1. And if you solve this by, say, plugging in x equals 0, 1, and negative 1, then what you find is that a is going to be negative 1, and b is 5/2, and c is negative 1/2. And so that tells you that my function, if I want to compute the integral of f of x dx, then I can write that as the integral of my a over x plus my b over x minus 1 plus my c over x plus 1 entire thing dx. And then integrating the pieces, we have minus ln absolute value of x plus 5/2 ln absolute value of x minus 1 minus 1/2 ln absolute value of x plus 1 whole thing plus c. For another example of the situation where you have to use polynomial long division, you should see page 485, example number 1. And I can't stress this enough, you always have to check that the numerator and denominator, the numerator has to have smaller degree than the denominator. Okay. Now, the general case we'll explore in the next slide. So, in the most general situation, you're going to have a polynomial function divided by another polynomial function, again where the numerator degree is strictly smaller than the denominator degree. And the method of partial fractions allows us to decompose that as a sum P1 over Q1 plus P2 over Q2 and so on, where the terms here come from the factors of the denominator. So in the previous pages we saw what happens when the factors of the denominator are all distinct and linear. The next case that occurs is when one of the factors of the denominator is a power of a linear factor. So if I have ax plus b raised to the n, then this contributes the following terms to the decomposition. So I have an a1 over ax plus b, like we did in the previous case. Then I have more terms, so a2 over the square of ax plus b, and then a3 over the cube, and so on up to ar over ax plus b to the r. And what you should note is that each of these can be integrated separately. For instance, we already know how to integrate the first term. What about something like, say, the third term? Well, the antiderivative of a3 over ax plus b cubed dx. So I would use u equals ax plus b. And that substitution would give me, since I have u to the minus 3 because of my denominator power, this would end up being a3 over a times negative 2 times 1 over ax plus b squared plus c. We'll see this in action in an example on the next page. So I want us to look at the example of integrating. Well, all we're going to do is we're going to write out the form for the partial fraction decomposition of the following function. So 1 over x times x plus 1 squared times x plus 2 cubed. Right? So I have three linear factors, x, x plus 1, and x plus 2, that are not multiples of one another, and some of them are occurring with exponents. So what you do is, to decompose this, you look at the distinct factors. So first we have this single factor of x, and that is going to contribute a over x. Next we have this factor of x plus 1 squared, and that's going to contribute two terms. I'll have b over x plus 1 plus c over x plus 1 squared. And then this third term that I have here is going to contribute three terms because I have a power of 3. I'll have d over x plus 2, and then another term for x plus 2 squared and another term for x plus 2 cubed. And then you would solve this if you were asked to do so, again clearing the denominators and setting up some linear equations. And you should look at page 488, example number 4, for another example like this. I want to move on to the next case. So we've seen what to do in all the cases where I have nothing but powers of linear factors in the denominator. So what happens if we have non-linear factors in the denominator? So if I have a factor in the denominator that is an irreducible quadratic, and I'll say what that means in a second, with no repetition, right? So just to a single power. So quadratic means that it's a degree 2 polynomial. That has no real roots. For example, x squared plus 1 is an irreducible quadratic because it is only taking on positive values, so it has no roots, and it has degree 2 because the largest power is x squared. Another example would be something like x squared plus x plus 5. That has no roots because if you try and use the quadratic equation, you'll end up getting imaginary numbers. Okay. And when you have a factor like this in your denominator, then this contributes the following term, one term of the form ax plus b over little ax squared plus bx plus c. Okay. And the point is that, again, if we want to integrate something like that, we can complete the square and then split it into pieces that will be of the form antiderivative of du over u squared plus a squared, or and antiderivative of u times du over u squared plus a squared. And what's the point there? The point is that in this situation we'll have 1 over a tan inverse of u over a plus c, and in this side you can use a u substitution of u squared plus a squared in order to get that this is 1/2 ln. This should be an absolute value, but since my denominator function is positive, I'll just have u squared plus a squared plus c. So let's see how this works in an example on the next page. So for instance, if I want to write out the partial fraction decomposition of the function 1 over x times x plus 1 squared times x squared plus 1 x squared plus 2, right? So I have one linear factor that's not repeated, one linear factor that's repeated, and then two irreducible quadratic factors. So this would have a decomposition of the form a over x for my first factor. My second factor contributes two terms, b over x plus 1 and c over x plus 1 squared. And then my first irreducible quadratic factor contributes denominator of x squared plus 1 and numerator of dx plus e, and then my second irreducible quadratic factor contributes another term like that, but with x squared plus 2 in the denominator. And if you were asked to find those constants, you would then clear the denominators and do the thing that we talked about before. This, when you have that many constants to solve for, it gets to be a real pain. So we're going to do a simpler example where we actually compute the integral. And I'm going to start that here. So here I have, let's rewrite that denominator a little bit. So I have x to the fourth plus x cubed plus 4x squared plus 2x plus 6 in the numerator, and I have x cubed plus 3x in the denominator, and I'm integrating that with respect to x. Now the first thing to note is that my numerator degree is too large, so I have to start with polynomial long division. And so the first question I ask in polynomial long division, what do I need to multiply x cubed by in order to get x to the fourth? And the answer is multiply by x. And I multiply through, and then subtract, and I end up at the next step with, oops, that should be an x to the fourth there, of course. So we end up with x cubed plus x squared plus 2x plus 6. And what do I need to multiply x cubed by in order to get x cubed is exactly plus 1. And when we multiply that through and subtract, we end up with our remainder being x squared minus x plus 6. So my integral that I'm interested in computing is going to simplify to the integral of x plus 1, that's my quotient, plus the remainder that I found, x squared minus x plus 6, divided by my original denominator, which I'll factor in a minute, all dx. Factoring that denominator, I can factor out an x, and the remainder, the leftover bits, exactly x squared plus 3, which is an irreducible quadratic factor. So when I want to decompose that fractional bit, so we'll look at x squared minus x plus 6 over x times x squared plus 3. I'm going to have two terms in the decomposition that come from the factors in the denominator. The first factor, x, will contribute a term a over x, and my second factor, x squared plus 3, is going to contribute bx plus c over x squared plus 3. Clearing the denominators like we've done previously, I'll multiply both sides of this expression by x times x squared plus 3, and we end up with x squared minus x plus 6 equals a times x squared plus 3 plus bx plus c times x. And we'll see on the next page how to continue with solving that. So we found that our equation for the coefficients in the decomposition, x squared minus x plus 6 equals a times x squared plus 3 plus bx plus c times x. Now here we have to be careful about using the technique of plugging in order to get answers. We'll be able to get some things this way. So if we use x equals 0 in order to make this bit vanish, then we'll end up with, on the left-hand side, 6 equals a times 0 plus 3 is 3 plus 0. Solving that, we end up with a equals 2, which is nice and easy. Plugging a equals 2 into our equation, we can now multiply this entire thing out and simplify. So we'll end up with x squared minus x plus 6 on the left-hand side, 2x squared plus 6 plus bx squared plus cx on the right-hand side. Collecting like terms, 2 plus b x squared plus cx plus 6. Notice that the 6's match up perfectly, and when we equate the coefficients of x squared and the coefficients of x, we end up with 2 plus b equals 1, so b equals -1, and c also equals -1 from the blue bits. So, our function decomposition that we had, remember that we were looking at x squared minus x plus 6 over x times x squared plus 3, and that's going to decompose as a over x plus bx plus c over x squared plus 3. And now I have my c, b, and a values to put in there. And back into my original antiderivative, let's call that I. So that was the antiderivative of x plus 1 plus this rational expression. So we have a equals 2 in the first bit here, so that's 2 over x, because down here I have 2 over x plus negative x minus 1 over x squared plus 3. That's using, again, these values that we found here. So back in the integral, we have minus x minus 1 over x squared plus 3 all integrated with respect to x. And we'll split that into some bits that we can integrate. Antiderivative of x plus 1 plus 2 over x, all of that is real easy. And now I'm going to break that last fraction into two pieces. Just by splitting the numerator. And now I have 5 bits that I can integrate rather easily. The fourth bit, I'm going to use a u substitution of u equals x squared plus 3. So that's here. And du equals 2x dx. So we end up for that with minus 1/2 ln of x squared plus 3. Again, the absolute value goes away because x squared plus 3 is positive. And the last one is going to be a tan inverse function, minus 1 over square root of 3 tan inverse of x over square root of 3 entire thing plus c. Again, that tan inverse integral that I got is from one of the formulas I had listed on the previous page. For more examples like this, see page 489 of the text, examples 5 through 6. Now, I recognize that this lecture is really bloody long, and that's because partial fraction decomposition has a lot of different cases. We're finally at the last case, and that's where you have irreducible quadratic factor raised to a power. So in this case, when you have something like ax squared plus bx plus c raised to the r power, this is very similar to what happened with the powers of a linear factor. You have a bunch of different contributions corresponding to the different powers of the factor of the denominator. So this will contribute the first term it'll contribute looks like the previous term, and now what we do is we have to take powers of that denominator until we get up to the power that we found in the decomposition. So as a last example, if I want to look at 1 over x squared times x squared plus 2x plus 1 times x squared plus x plus 2 cubed. Now this one's a little bit subtle. The thing that you have to note, this is not irreducible. because that one factors as x plus 1 squared. But this one is irreducible, which you can see when you take the quadratic formula, you end up with complex roots. And so we'll simplify this. This is 1 over x squared times x plus 1 squared times x squared plus x plus 2 cubed. And so the partial fraction decomposition in this case has the form, I have two terms corresponding to the power of x. I have two terms corresponding to the powers of x plus 1 squared. And I'm going to have three terms corresponding to that third power of my irreducible quadratic. So we'll have ex plus f over x squared plus x plus 2 plus gx plus h over the square of that. Lastly, plus ix plus j over x squared plus x plus 2 cubed. And you can see more examples like this, examples 7 through 8 in the text. And you should also take a look at example 9, which deals with what we call a rationalizing substitution. This is the end of the extremely long lecture on section 7.4, partial fraction decompositions.